Buildings, they're not supposed to move, but these do, twisting, sliding, and reshaping themselves like machines. Today's video, I'm going to count down 15 incredible moving buildings. Starting with number 15, the Dynamic Tower in Dubai. The Dynamic Tower is a proposed 80-story skyscraper in Dubai designed by architect David Fisher. Now, what sets it apart is its ability to move. Each floor is planned to rotate independently, allowing the entire building to change shape continuously. If it's completed as envisioned, it would be the world's first rotating skyscraper. The concept includes prefabricated floors manufactured off-site and then attached to a central core. Each floor would be capable of completing a full rotation every 90 minutes, powered by wind turbines installed between each level. The tower's rotation would allow residents to have a 360-degree view of Dubai without leaving their apartments, which is pretty nice. By using voice commands, occupants could control the direction and speed of their unit's rotation, and the design includes features for horizontal wind turbines and solar panels that would make the building energy self-sufficient. According to the architect, as many as 79 wind turbines could be positioned between the floors to harness energy from the constant desert wind. Despite the innovative nature and media attention since the announcement in 2008, the Dynamic Tower has not yet been built. The project has faced delays due to funding, engineering complexities, and regulatory hurdles. Critics have questioned the structural integrity of rotating floors and the feasibility of aligning mechanical, electrical, and plumbing systems within a constantly moving building. However, if completed, it would mark a significant leap in technology and modular construction. The building would not have a fixed shape, but rather a constantly changing silhouette. Now, this principle of movement integrated into architectural design has drawn some interest from developers. Even though the building hasn't broken ground, it does continue to serve as a conceptual reference point. The Dynamic Tower represents a future where architecture isn't static. While most skyscrapers are fixed in form, this one proposes a world where a building becomes a moving object that interacts dynamically with its environment. Whether or not it's eventually constructed, though, its concept has already influenced other adaptive and kinetic design projects in the world. Number 14, the Albahar Towers in Abu Dhabi. The Albahar Towers in Abu Dhabi are a pair of 25-story office buildings that feature one of the most advanced examples of responsive architecture. Completed in 2012, they serve as the headquarters for the Abu Dhabi Investment Council and are located along a major highway in the capital city. Now, what sets it apart is the dynamic facade, a system of 1,036 geometric sunshades that open and close in response to the sun's position, effectively giving the towers a moving outer skin that adjusts throughout the day. The towers were designed by ADIS architects in collaboration with the engineering firm Arup, and the goal was to create a building that reflected the local cultural heritage while also addressing the intense desert climate. The design of the sunshades was inspired by the traditional Islamic ornamental wooden screens used in the Middle Eastern architecture to filter sunlight while allowing air circulation. Each one is made of a lightweight fiberglass frame with translucent Teflon-coated mesh membranes. They're mounted to a steel frame that wraps around the cylindrical tower and are individually motorized. Controlled by a building management system connected to sun tracking software, the shades open or close automatically depending on the time of day and angle of sunlight. This system helps reduce solar gain by up to 50%, and it minimizes the need for air conditioning. The movement of these shades is subtle but constant. At any given moment, different parts of the facade are shifting, rotating, or closing in coordinated motion to create an undulating effect across the tower's surface. This gives the appearance of a living structure, one that continuously is adapting to its surroundings rather than remaining static. The energy efficiency of the building is significantly improved by this design. The architects estimate that the responsive facade reduces cooling load by over 20%. Additionally, the towers incorporate other sustainable features like gray water recycling, occupancy-based lighting, and low emissivity glazing. These towers have received international acclaim for combining cultural design elements with advanced engineering. They won the Council on Tall Buildings and Urban Habitats Innovation Award in 2012 and are frequently referenced in architectural literature as a leading example of kinetic environmental control. Rather than relying solely on fixed insulation or heavy tinting, these towers demonstrate a future-forward approach, a structure that moves in real time to deal with climate. The towers reflect a broader trend in architecture towards adaptive building skins, particularly in regions with harsh climates. By merging traditional aesthetics with modern technology, the towers show that kinetic movement in buildings can serve both functional and symbolic roles, delivering comfort, reducing energy use, and making a strong visual statement in the skyline. Number 13. The Falerkirk Wheel, Scotland. The Falerkirk Wheel is the world's only rotating boat lift located in central Scotland. Opened in 2002, it was built to reconnect the Forth and Clyde Canal with the Union Canal, which had been disconnected since the 1930s. Prior to the wheel's construction, a series of 11 traditional locks would have been required to bridge the 79-foot difference in height between the two canals. The Falerkirk Wheel eliminates the need for these locks by lifting boats using a massive rotating mechanism that looks and operates like a giant mechanical sculpture. The wheel stands 115 feet, that's 35 meters tall, and it connects to a tunnel that leads directly to the Union Canal. Boats enter one of two opposing gondolas filled with water. These gondolas are balanced using the principles of Archimedes, which states that a floating object displaces its own weight in fluid. This means that whether a gondola holds just water or water plus a boat, the total weight remains equal, allowing for a smooth, balanced operation. When activated, the wheel rotates a full 180 degrees in just 5 minutes. It uses surprisingly little energy too, approximately the same amount required to boil 8 kettles of water. Well, thanks to the balanced nature of the system, the rotation is driven by 10 hydraulic motors that power a central ring gear. The wheel's rotation is slow, precise, and it ensures stability and safety for passengers and boats. The engineering behind it was developed through collaboration between architectural and engineering firms, and construction took about 3 years and required an investment of around £17.5 million. The project was part of a larger £84 million initiative called the Millennium Link, designed to revitalize Scotland's canal infrastructure. Since opening, it's become a functional part of their canal system and a popular tourist spot. One of the key technical challenges, though, during the design phase was ensuring perfect synchronization between the two arms and the gondolas. Any imbalance could lead to mechanical failure or structural stress, and this was addressed by using precision gears, digital monitoring systems, and a robust braking mechanism to control and stabilize the movement. The Falerkirk Wheel has a significant impact on the region. It's drawing hundreds of thousands of visitors annually, and it's contributed to the economic revitalization of Falerkirk. In addition to boat rides, though, the visitor center offers exhibits about the wheel's construction, environmental impact, and the history of the canal system. The structure is built to last. It's constructed with over 1,000 tons of steel, and it's set with reinforced concrete foundations. Because of its innovative design and energy efficiency, the wheel is frequently cited in engineering literature, and it's won multiple international awards. It demonstrates how mechanical movement can be integrated into large-scale public infrastructure to solve practical problems in a novel way. Number 12. The Sliding House, England. Located in Suffolk, England, the Sliding House is a private residence designed by architecture firm DRMM and completed in 2009. At first glance, it appears to be a conventional rural home with clean lines and timber siding. However, the most notable feature is a mobile outer shell that can slide along tracks to cover or expose the main structure beneath. This moving exterior allows for dynamic environment control, altering light, temperature, and privacy according to the homeowner's preference. The house consists of 3 aligned elements: the main residence, an annex for guests, and a garage. Over these sits a separate outer shell constructed of timber and designed to move along a 28-meter-long rail system. The shell, which resembles a barn in appearance, is powered by an electric motor and can fully enclose the main house or slide back to reveal glass walls and modern finishes. The movement itself takes about 6 minutes from one end to the other. The sliding mechanism, though, serves several purposes. It provides insulation during colder months, offers protection from the wind and rain, and gives privacy from nearby roads. When retracted, it allows natural light to flood the house through floor-to-ceiling glass panels. This makes the house adaptable to the seasons and changing weather, reducing the need for artificial heating and lighting. The idea behind it was to challenge the traditional notions of what a house should be. Rather than being a static object, the sliding house demonstrates how architecture can adapt to its environment in real time. The designers drew inspiration from agricultural buildings in the region, many of which are built in modular fashion to be flexible and reconfigurable. They wanted to create a house that responds to its context while offering the comfort and functionality of a modern home. Since its completion, the sliding house has received widespread attention in publications and exhibitions. It's been featured on television programs and won multiple awards for innovation. It shows how mobility can be used in architecture, not just for spectacle, but for functional living improvements. By adjusting its form in response to weather, lighting, or the homeowner's mood, it challenges the idea of buildings as fixed objects. This kind of responsive architecture is becoming increasingly relevant in an era when environmental considerations and energy efficiency are major priorities for some people. Number 11. The Milwaukee Art Museum, Wisconsin. The Milwaukee Art Museum in Wisconsin. It's one of the few institutions in the world with a massive moving architectural component built into its design. The museum's Quadrachi Pavilion, opened in 2001, was designed by Spanish architect Santiago Calatrava. Its most striking feature is the Brise Soleil, a movable sunscreen structure with a wingspan of 217 feet, that's 66 meters, that opens and closes like a bird's wings, giving the museum a dynamic identity that changes throughout the day. The Soleil consists of 72 steel fins mounted to a pair of hydraulic arms. Each fin varies in length, with the longest reaching up to 105 feet, that's 32 meters, and when fully open, the structure resembles a bird in flight. The wings open in the morning, close during inclement weather or high winds, and shut again at night. This process of opening or closing takes about 3.5 minutes, and it's powered by computerized hydraulic systems. Beyond aesthetics, though, the moving wings do serve a functional purpose. When extended, they provide shade and reduce solar heat gain in the glass-walled reception hall below. This helps maintain a more stable interior temperature and reduces energy use. When retracted, the building is less exposed to potentially damaging high winds coming off Lake Michigan. Calatrava's design was the result of an international competition held in the 1990s. His winning concept was inspired by natural forms, of course, specifically the motion of birds and the nautical atmosphere of Milwaukee's lakefront. The wing-like structure has become an iconic part of the city's skyline, and it's elevated the museum's global recognition. From a technical standpoint, it is a feat of precision engineering. The mechanisms have to account for not only the significant weight and reach of the wings, but also the torque and forces generated during movement. The system is regularly maintained, of course, and it's got a backup hydraulic circuit in case of mechanical failure, and despite its complexity, it's proven highly reliable over more than 2 decades of operation. Inside the pavilion, the museum's Windover Hall is equally notable for its openness and light-filled design. That building's movable exterior is fully visible from the interior, creating a strong connection between their contents and the natural environment outside. Visitors can watch the wings unfold from the inside and add an experiential component to the museum visit that bridges architecture and engineering with art. The Milwaukee Art Museum's movable Brise Soleil. It's a rare example of a kinetic architecture integrated into a major public institution. The daily motion here turns a static building into a dynamic one, and it highlights how movement can be used in architecture not just for novelty, but for environmental performance, symbolic design, and of course, user experience. Number 10. The Tetro del Agua, Spain. The Teatro del Agua, the Water Theater, officially known as the Auditorio del Tenerife, is a performing arts venue located in Santa Cruz de Tenerife, one of Spain's Canary Islands. Completed in 2003, the building is famous for its distinctive design by Spanish architect, again, Santiago Calatrava. One of the most unique aspects of this one is the moving architectural element, a huge sweeping concrete roof that seems to float above the building and rises dramatically into the sky. While the roof itself doesn't open and close like a mechanical door, parts of the structure are capable of slight mechanical movement to allow for adjustment and maintenance, and the illusion of movement is a key feature of the design. Though it's not technically a fully kinetic structure in the sense of being motorized like some of the other entries, the building does deserve recognition for how it uses balance, cantilevered engineering, and structural stress to create a sense of motion and tension. This giant curving canopy, known as the wing, projects 50 meters over the building, and it appears to hover unsupported. It is in fact held in place by a complex internal system of cables and reinforcements that allow it to shift slightly under wind load. The scale of the wing and the curve create optical illusions that give the impression that it's constantly in motion, especially when viewed from different angles or when the sun casts moving shadows throughout the day. This integration of movement into the visual language of the building, without relying on motors or electronics, is an example of how architecture can imply motion through form. The building itself, though, hosts the Tenerife Symphony Orchestra, and it's used for opera, dance, and other performances. The shape and thickness of the roof were designed not only for aesthetics, but also to enhance the acoustic performance by shielding the space from external noise. The building has become one of the most recognizable landmarks in the Canary Islands. Its combination of formal dynamism and subtle structural movement shows a different kind of kinetic architecture, one that doesn't need to be motorized to suggest flexibility. While not a kinetic structure in the traditional sense of gears and motors, this theater is an example of engineered flexibility. The design accommodates movement where necessary and creates a strong visual impression of motion through balance, curvature, and materials. It broadens the definition of a moving structure by showing how buildings can shift, breathe, and adapt, even when their movement is nearly imperceptible. Number 9. The One Ocean Pavilion, South Korea. The One Ocean Pavilion, located in Yeosu, South Korea, was built as the main corporate pavilion for the Expo 2012, and it's one of the most visually striking examples of kinetic architecture. Designed by the Austrian firm Soma Architecture, the building features a dynamic facade composed of 108 kinetic fins that open and close to regulate light and temperature. The fins are constructed from glass fiber reinforced polymers and are individually motorized, allowing the building to adjust its skin in response to sunlight and conditions throughout the day. The fins are mounted vertically and curve outward from the structure's surface, giving the pavilion an organic, flowing appearance that resembles waves or ripples. When the sunlight is too strong, the fins close to provide shade. When the light is less intense or when ventilation is needed, the fins can open to allow more natural light and air into the building, and each fin moves independently. Structurally, the building uses a lightweight steel frame clad in composite panels, and these kinetic fins are attached to a secondary exoskeleton that's offset slightly from the main building. This separation allows the fins to move freely, of course, without interfering with the main structure. The pavilion was designed to align with the Expo 2012's theme, the living ocean and coast. The moving exterior evokes marine life, specifically organisms like mollusks and fish that open and close their shells or fins. While the inspiration is biological, the engineering is entirely mechanical and programmable. The system can also be manually overridden if maintenance or specific visual displays are required, and inside the pavilion features interactive exhibits focused on marine biodiversity and sustainable ocean use. This dynamic shading system not only serves a functional energy reduction purpose, but it also makes the structure part of the exhibit itself, demonstrating how buildings can respond to their environment in real time. The One Ocean Pavilion, it shows how adaptive movement in buildings can be used not only for visual effect, but also for climate control, sustainability, and thematic expression. Its use of moving parts is not decorative, it is integral in how the building functions and presents itself to the public. Number 8. The BMW Velt Double Cone, Germany. The BMW Velt, located adjacent to the BMW headquarters in Munich, Germany, is a multifunctional exhibition and event facility designed by Coop Himmel and completed in 2007. Among its most notable features is the double cone structure, a dramatic glass and steel form that not only serves as a symbolic centerpiece, but also incorporates mechanical elements that move as part of the building's lighting, environmental, and event systems. While the double cone itself is a fixed structural feature, parts of the building's interior infrastructure, including suspended platforms, lighting grids, and exhibition modules, are designed to move, allowing the space to be reconfigured. The double cone is a 28-meter-tall spatial structure made of steel and glass, twisting as it rises and creating the illusion of motion even when stationary. Within the space, overhead tracks and rigging systems are installed to allow sections of lighting arrays, display equipment, and presentation booths to be raised, lowered, or rotated, or removed altogether depending on the needs. The kinetic elements, though, are not simply stagecraft, they are embedded into the architecture. For example, the lighting rigs contain motorized joints and rails, which allow the staff to program different lighting effects and change spatial configurations without requiring scaffolding or extensive labor. BMW Velt is not a museum, but it's a customer-facing experience center that includes vehicle delivery, interactive product displays, and brand exhibitions, and as such, the kinetic infrastructure here plays a central role in how the space operates. For vehicle reveals, a car can be hoisted onto a platform using a concealed lift, and modular backdrops can be moved or rotated to change branding between events. These mechanical systems are integrated into the building's floor and ceiling grid. And while the building itself is static in form, the interior environment is dynamic. It's engineered to respond to rapid changes in use, from quiet individual car pickups to large public events and exhibitions. The combination of this high-tech infrastructure with the symbolically kinetic architectural language shows BMW's brand identity, precision, engineering, and motion. The double cone structure and its integrated moving systems serve as both functional elements and branding tools. They show how kinetic architecture can support operational flexibility in commercial settings. BMW Velt uses movement strategically, not for spectacle, but for reusability and optimized user experience. Moving on to number 7, Maison Vert, the Glass House in Paris, France. Maison du Verre, or the House of Glass, is one of the earliest and most innovative examples of kinetic architecture. It was built between 1928 and 1932 in Paris by architect Pierre Charot. The structure integrates mechanical elements and movable components into a residential environment in ways that were radically ahead of their time. Now, what makes it unique is not the outward mobility, but the precision of which internal components are engineered to move and reconfigure for changing purposes throughout the day. Large sliding walls, retractable panels, hinged ventilation systems, and pivoting furniture all transform the space and experience of the building. Even the entrance features a concealed mechanized trapdoor and a pulley system to manage access while maintaining security, of course, an early form of adaptive architecture. The facade is composed of translucent glass blocks supported by a steel frame, allowing diffuse natural light into the interior while maintaining privacy. The wall doesn't move, but inside nearly every part of the home structure is adjustable. Bookshelves on rails, sliding ceiling screens, fold-out furniture, and even staircases made of steel mesh are designed to be physically manipulated with minimal effort. Maison du Verre was originally built as both a doctor's office and a private home. The kinetic elements allowed the doctor to shift between clinical and residential environments seamlessly. Patients and family members could be directed or isolated, depending on the need, and this hybrid use case was rare at the time, and it helped pioneer the idea that a building could be functionally dynamic. Many of the mechanisms in the structure are manually operated, relying on levers, counterweights, and tracks, which gives the house a tactile quality, one that bridges the gap between architecture and machinery. Today, it remains a private residence and it's not open to the general public, though limited academic tours are sometimes granted. This building's ability to physically adapt without losing its spatial coherence has inspired countless architects to rethink how static structures can become responsive without needing digital systems. Now, while not moving in the way a kinetic sculpture or fold-out stadium might, Maison du Verre earns its place on this list for integrating movement into the daily life of a building. Its design challenges the boundary between fixed and flexible, offering a model of human-centered mobility that remains relevant almost a century later. Number 6. The Media TIC building in Spain. Located in the technology district of Barcelona, the Media TIC building is a high-tech office and innovation center designed by Enric Ruiz Gelli and completed in 2010. It incorporates one of the most advanced active facades in Europe and features a kinetic envelope that adjusts to environmental conditions to reduce energy consumption. The building's exterior is composed of a system of transparent plastic cushions that inflate and deflate to regulate solar gain, temperature, and daylight. The building spans about 8,500 square meters, and it was designed to house digital businesses and research facilities. Its south and west facades are fitted with a triple-layered ETFE system, that's that plastic, that uses compressed air to inflate or deflate each pillow. When the sun's really intense, the outer layer can become more opaque by introducing printed patterns or by adjusting air pressure. This allows the facade to act as a dynamic thermal barrier that responds to heat and light throughout the day. Sensors on the roof and building perimeter monitor real-time conditions, and based on that data, the centralized computer system sends commands to the pneumatic equipment to adjust the air pressure. These changes are subtle but continuous, ensuring that the building maintains optimal temperature and lighting levels. Now, structurally, it's built around a steel framework with minimal internal supports, allowing for an open interior space. The kinetic facade acts like a secondary skin, suspended from the main structure and linked via aluminum frames and steel cables. The ETFE cushions are extremely lightweight and durable, and they're able to withstand winds and high loads of temperature variations without tearing or degrading. The building was awarded the World Architecture Festival's Building of the Year in 2011 for its sustainable design, and it achieved a LEED Gold certification and has become a model for energy efficiency. Inside the building, it includes co-working spaces, meeting rooms, exhibition areas, and media labs, and its open-plan layout benefits from natural light managed by the kinetic skin. The thermal regulation tube provided by the facade significantly reduces their carbon footprint by minimizing the need for artificial cooling. This building is a prime example of how kinetic architecture can address climate challenges in urban areas. Instead of relying on static solutions like fixed shades or heavy insulation, it uses movement to adapt in real time. This building does kind of redefine what a smart building can be. It doesn't just monitor conditions, it reacts to them. The result is a high-performance structure that achieves both visual interest and a measurable energy savings through continuous movement and adaptation. Number 5. The Kansas City Public Library Parking Garage, Missouri. The Kansas City Public Library Parking Garage. It is one unconventional moving structure, though its movement is more conceptual than mechanical. Located in downtown Kansas City, Missouri, the garage features a facade designed to resemble a giant bookshelf with spines standing nearly 25 feet tall and 9 feet wide. Now, while the garage itself doesn't rotate or transform like some kinetic buildings, several components of its operational structure allow for dynamic movement. Completed in 2004, this garage was part of a revitalization plan for Kansas City's downtown area. It serves the adjacent Kansas City Public Library's Central Branch, and it was designed with strong community input. The facade's book spines were chosen through a public vote, with titles ranging from To Kill a Mockingbird to Fahrenheit 451. But the idea was to reflect the values of literacy, learning, and community through an iconic visual statement. The garage has 5 levels and holds over 500 vehicles. It's one of the most distinctive operational elements here is the use of dynamic entry and exit controls. It uses an adaptive traffic control system that changes the direction of interior traffic flow based on time of day, event schedules, and peak usage. For example, during large events at the nearby Sprint Center or library programs, traffic signals, signage, and lane allocations all shift in real time to improve efficiency and prevent congestion. Additionally, it uses retractable barriers and adjustable gates to manage the flow. Now, those components can physically alter the configuration of lanes and parking areas, effectively changing the structure's interior layout multiple times a day. Another area where movement plays a role is in the ventilation and lighting systems. Huge ventilation fans are programmed to adjust based on carbon monoxide levels detected by sensors throughout the facility. Likewise, the lighting system is motion sensitive and reacts to occupancy, with brighter illumination activated only in zones currently in use. This approach reduces total electrical load and it prolongs the life of the fixtures. One of the most interesting aspects of the garage is the elevator system. It's designed to minimize wait times. It uses a destination dispatch system that groups passengers going to the same or nearby floors, optimizing movement and reducing stops. This system relies on real-time algorithms and user input panels placed outside the elevator cars. By pre-sorting the users, the elevators can reduce energy usage and improve vertical circulation speed, a small but crucial optimization in a high-traffic structure. Furthermore, the building's management systems integrates with citywide traffic and event databases. When a major event is scheduled nearby, the system receives fresh data and can pre-configure the garage's flow. Though the structure is not kinetic in the traditional sense of spinning, unfolding, or changing shape, it embodies a broader concept of architectural movement, the capacity to adapt, reconfigure, and respond in real time to human needs and environmental conditions. The movement is systemic, infrastructural, and procedural. It redefines what a moving structure can be by blurring the lines between smart technology and architecture. Its facade not only serves as a landmark, but also turns a mundane necessity into a celebration of literacy and civic pride. The visual movement suggested by the giant book spines combined with the operational motion behind the scenes makes the Kansas City Public Library parking garage one of the most understated, yet incredible moving structures in use today. Number 4. The Morpheus Hotel, Macau, China. The Morpheus Hotel in Macau is an example of modern architecture that integrates structural movement through form and innovative engineering rather than literal motion. Designed by the late Zaha Hadid and completed in 2018, the building is part of the City of Dreams complex and it's known for its futuristic appearance. While the building doesn't feature large-scale mechanical movement like rotating walls or shifting facades, the internal configuration and load-bearing structure are designed to facilitate dynamic flows of people, light, and air. At its core, the hotel's most distinctive feature is the exoskeleton. This is a structural steel mesh that wraps around the building's exterior and supports it entirely. The design includes two voids cut through the center of the building, creating a pair of free-form curves that also make the hotel appear to be sculpted out of a single mass. These voids aren't just for aesthetics, they also serve practical functions, creating internal bridges, sky lobbies, and circulation channels that enable vertical movement across the hotel's 40 stories. The idea was to create a structure that moved visually and spatially. Guests traveling from one side of the hotel to the other can walk along glass-enclosed bridges suspended inside the voids. The bridges are part of a network of circulation paths and encourage movement across unconventional trajectories, like curved ramps, elevated walkways, and panoramic elevators. The elevator system is one of the hotel's more technical kinetic elements. Morpheus uses high-speed elevator networks managed by an intelligent dispatch system. One of the elevators travels at an angle through the central void. That's a rare feature that enhances the experience and adds a dynamic sense of movement for the guests. Lighting and shading systems within the Morpheus also exhibit kinetic characteristics. Programmable LED systems adjust based on the time of day, events, and occupancy patterns, and it includes smart glass panels that can modulate tint levels in real time. Though these systems are not externally visible, they function as embedded movement technologies that adjust a building's interaction with the environment. Structurally, the project required some advanced solutions. The exoskeleton supports both gravity and lateral loads and allows the core of the building to remain largely unobstructed. The steel mesh exterior was prefabricated in segments and assembled on site, and its design had to be rigorously tested for seismic performance due to Macau's coastal location. The hotel is more than just a high-end destination. It's a study in how architecture can communicate motion through structure and spatial experience. The movement is implicit, felt through circulation, through the building's continuously morphing visual perspectives. The result is a building that moves conceptually and experientially, challenging the static norms of high-rise construction. The project has won numerous architectural awards and is widely recognized as one of the most technologically advanced hotel buildings in the world. And while it doesn't feature rotating facades or retractable roofs, it shows how a building can be kinetic in a more abstract architectural sense by channeling flows of people, light, and air through open, adaptable space. Number 3. The Seattle Central Library. The Seattle Central Library, completed in 2004 and designed by Dutch architect Rem Koolhaas and the firm OMA in collaboration with LMN Architects, is one of the most significant examples of dynamic public architecture in the 21st century. While the building doesn't physically move, it is designed to be intentionally flexible, layered, and organized to encourage constant human motion. This kind of adaptability represents a different category of kinetic architecture. Rising 11 stories and occupying a full city block in downtown Seattle, the library challenges a traditional notion of a library as a static archive. The layout is based on a continuous spiral of information that ascends gradually through the building, allowing patrons to browse the entire nonfiction collection without climbing stairs. That concept, called the book spiral, is implemented through a 4-story ramp that winds through the building's midsection. It shows a philosophy of uninterrupted motion, encouraging users and readers to move naturally from one section to the next in a continuous way. The exterior is a glass and steel skin that's formed into an irregular angular mesh. Now, the form is not simply for aesthetics, it does maximize natural light and provides view of the city, and it allows the building's interior programs to define the shape, not the other way around. The grid system is used for the facade that adapts to internal zones, including the reading room, staff areas, and public meeting spaces, and it creates a building that reflects internal dynamics rather than imposing an external order. Now, one of the library's kinetic components is the use of transformable spaces. Meeting rooms, regular zones, and event areas can all be reconfigured using retractable walls, movable partitions, and modular systems. This allows the library to adapt in real time to demands, accommodating a small poetry reading 1 hour and a 200-person community meeting in the next. Lighting, audio, and projection systems are integrated into movable ceiling panels, and that ensures the space is functional no matter how it's arranged. But perhaps most significantly, this library is designed to be flexible. When opened, it included a floor dedicated entirely to digital learning. That's a rare feature at the time. As public needs have shifted, though, parts of the building have been reprogrammed to serve as maker spaces, digital studios, and collaborative work areas. This capacity to change use over time without altering the building's structural core makes it a model for long-term adaptability. Yeah, it's not a kinetic building in the traditional sense, but it behaves like one through its responsiveness to the user needs, its emphasis on circulation, and its programmatic evolution. Ultimately, the library demonstrates how a building can be in motion without moving parts. It invites users to keep moving, keep learning, and keep reconfiguring the space around them. It's a machine for civic engagement and the ever-evolving infrastructure of knowledge, and a landmark of dynamic, forward-thinking design. Number 2. The Institut du Monde Arabe, France. The Institut du Monde Arabe in Paris, completed in 1987, is one of the earliest and most important examples of kinetic architecture. The building features a distinctive south-facing facade composed of 240 light-sensitive mechanical apertures. These apertures, geometric diaphragms that resemble camera shutters, open and close automatically to regulate light and heat. This kinetic system was inspired by traditional Islamic screens, which use intricate patterns to filter the sunlight while preserving your privacy. In this modern adaptation, each diaphragm was controlled by a computer system that adjusted their positions throughout the day based on sunlight intensity. The result was a constantly shifting facade that both reduced glare and cast dynamic patterns across the building's interior spaces. The diaphragms were built using aluminum and steel components and connected to photoelectric sensors and small motors. Although many of the original mechanisms became inoperable, some were later restored, and the building remains a landmark in adaptive facade design. Inside, the building houses a museum, a library, auditorium, and office space, and the kinetic facade dramatically improves energy efficiency. The changing light conditions do contribute to a unique visual atmosphere in there that evolves throughout the day. This project won the Aga Khan Award for Architecture in 1989, and it influenced a generation of architects interested in this responsive architecture. It proved that movement in architecture could serve as a real environmental function, not just visual impact. And while many later kinetic buildings use digital controls or robotic mechanisms, the Institute here pioneered the integration of analog mechanics and cultural symbolism. The building still stands as a key example of how kinetic elements can blend aesthetics, tradition, and function. It doesn't just look different, it behaves differently, offering a glimpse into architecture that adapts and responds like a living organism. Number 1. The Shed, New York City. The Shed. It's a cultural venue located in New York City's Hudson Yards, opened in 2019 and designed by Diller Scofido, Renfro, and Rockwell Group. What sets the Shed apart is the massive, movable shell, a telescoping outer structure that can extend or retract to adapt to the building's footprint. This allows the Shed to transform from a smaller indoor venue to a large performance space in just minutes. The kinetic shell is built from a steel diagrid frame covered in polycarbonate panels, which are lightweight, insulating, and transparent. It rides on 8 6-foot diameter wheels that run along rails embedded in the plaza, and a single operator can extend or retract the structure using a rack and pinion drive system. When deployed, the shell covers the McCourt space, a 17,000-foot square area that can host concerts, installations, or public events. Inside the permanent structure are flexible galleries, a theater, and studio spaces. These are designed to be reconfigured with modular walls, retractable seating, and convertible lighting. This adaptability matches the exterior's physical movement, allowing the building as a whole to respond to diverse artistic needs. The kinetic design isn't just for show here, it's functional. The Shed can resize itself depending on the scale and type of event, maximizing space in a dense urban setting. It represents a new direction in architecture where buildings don't just house culture, but they actively support it by transforming in real time. The Shed. It demonstrates how architecture can be physically dynamic, not just visually interesting. It's a fully operational machine for creativity, one that literally moves to accommodate the future of performance and art.